Welcome back to RobotGeek 101. In previous videos we saw how to center our servos. Now we're going to learn how to control our RobotGeek servos in the Arduino environment. Let's take a look at what you can do with RobotGeek servos. Here we've got a really basic pan and tilt kit. On our kit we've got a laser and a camera mounted to the top. By using one servo we have our pan, and our second servo on top gives us our tilt. So this is really cool for vision tracking. Having this laser, we can mount just about anything we want in this pan tilt kit and then use the servos to actuate and move that object. We could even put this foam dart gun on our turret. As you'll see, there's a servo right here, and by controlling the angle of the servo back and forth, we can fire the gun. Here you've got a RobotGeek snapper arm with 5 different servos. We've got one in the base that gives us our rotation, much like the pan tilt kit. Then we've got here this tilt servo, so to speak, but in a sense we have 3 tilt servos, and these 3 joints allow us to do a lot of different movements in the robot arm. Finally, we also have a servo right in here that actuates the gripper. So as the servo turns and closes, the gripper will close. So in this setup we've got one of our servo test rigs that we use internally to check some of our servos. Normally it has some more buttons for testing, but for this video all we need is the knob and a single push button. We have our servo. It's already been centered, and we have this needle on here to make it easy to see the different degrees that the servo can go to. We also have our Geekduino and sensor shield. We've made sure that our jumpers are set to V in for our pins 3, 5, and 6 because we have our servo plugged into 3. So this servo will be getting power from our 6-volt power supply. We've also got our micro USB plugged in. We've got our push button plugged into DIO2 and our knob plugged into analog 0. Just like in the PWM video, we have this logic analyzer. This is not something that you need in your setup, but we'll just be using it to show some of the different signals coming out of the Geekduino. Now, this code is actually still running the centering code from video 1, so if we reset the Geekduino board, the servo is going to move to those positions and then back to center. So let's go to Arduino IDE. We'll go File, Sketchbook, RobotGeek Sketches, RG101, 05 Servo, A, Servo Degrees. So the Arduino has a library, servo.h, that we can include to control servos. This #include is just a way to call external files. So the servo.h lives in the Arduino IDE, but we have to explicitly call it to get all of the servo functions. We have our constant integer servo pin, number 3. Here's where we are calling the servo class. So we're creating this object, servo1. This object is going to be the stand-in in our code for our actual physical servo. In our setup, we have servo1.attach. So attach is a function, much like pin mode, but attach will only work on a servo object. So that's why you have this relationship where it's servo1.attach servo pin. If I were just to have attach servo pin, this code wouldn't work properly because it doesn't know where to attach the servo pin to. So the syntax will always be servo1 dot and then the function that goes to the servo. So this attach tells digital pin 3 that it's going to be set as a servo pin. There's a servo connected and gets it ready to receive servo signals. We've got another servo specific function, servo1.write. So the write function expects a degree input as its parameter. So here I'm going to write 0. So the servo is going to move the needle to about 0 degrees. I'm going to then wait 3 seconds. I'm going to servo write 90. That's going to bring it up to the middle, 90 degrees. Then servo1.write 180. Bring it over here to 180. Now, one thing to keep in mind is with an RC servo like this, you're never going to get absolute accuracy. So when you tell it to go to 0, it might shoot past a little bit or hover right around it. Same with 180, it's going to come all the way here. Since you align to 90, your needle should always be pretty close to 90, but at the outer edges you might see a little bit of difference from the angles that you're expecting. Our loop isn't running anything, and that means that this is just going to run a single time. So let's go ahead and upload this. So there we moved to 0, waited 3 seconds, moved to 90, waited 3 seconds, moved to just about 180. As you can see, we're a little bit past 180. If we wanted to see that again, we'd have to reset the board, go to 0, wait for 3 seconds, go to 90, wait for 3 seconds, go to 180. Now, the servo.write function is nice because you have your degrees, but it does cause a couple of problems. One is in the background of the Arduino IDE, it uses some sort of strange numbers, and the other part is that you don't get as much resolution as you do if you were to talk to the servo in its native communication type. And that's where we get into write microseconds. So let's go to File, Sketchbook, RobotGeek Sketches, RG101, Servo, Servo Microseconds. So first thing, let's go ahead and upload this. We'll see the behavior. Just like before, we go to 0, we go to 90, and then we go to 180. Just like before, we're including servo.h. We've got our constant integer servo pin 3, servo variable servo 1. We're attaching, we're writing 3 times, we're delaying. But now, instead of write, we have write microseconds. So write microseconds is sort of a mix between analog write and delay microseconds. We basically define how big a pulse should be in microseconds. So here you can see I'm defining a pulse of 600 microseconds. That's 0 degrees. Here I'm defining a pulse of 1500 microseconds. That's 90 degrees. And 2400 microseconds is 180 degrees. So I'm going to go ahead and bring up our logic analyzer. I'm going to change this to 10 seconds. Then I'm going to go ahead and reset the board and start reading data. So here you can see a pulse. It looks a lot like our pulse width modulation pulses. We have a period of 20 milliseconds, so each cycle takes 20 milliseconds. Our single pulse here is 0.6 milliseconds, so that's 600 microseconds. So these pulses are telling the servo to go to 0 degrees and to stay at 0 degrees. Now let's move a little bit further. Here, just after 3 seconds, we see 1.5 milliseconds. So that's our 1500 microseconds. So this is where we're telling the servo to go to 90 degrees. And as you can see, our period is still 20 milliseconds. So each cycle still takes 20 milliseconds. And if we go all the way to the end, our cycle is now 2.4 milliseconds, or 2400 microseconds. But the period is still 20 milliseconds. So as you can see, when our period is 20 milliseconds, and we zoom out, these look pretty similar, but very tiny increments from 600 microseconds up to 2400 microseconds make a large amount of difference in what angle the servo is set to. All of the RobotGeek code is going to use this write microseconds convention. We will have some formulas for you to convert microseconds to angles depending on exactly how you're working with your code. But like I said, having this larger band gives you better resolution, your calculations will come out better, and just gives you better control over your servos. Our servos run from 600 to 2400, at least the RobotGeek servos do, and it just gives you the full band without having to worry about problems or exactly what microseconds you're sending to the servo. So let's take a look at our next sketch. We'll go File, Sketchbook, RobotGeek Sketches, RG101, Servo. We're going to do Analog In, Servo Out. This sketch, as you can guess, is going to use our analog pin. So we've got our analog pin on 0. We have our servo pin set to 3. Here we're defining our min, max, and center pulse so that we can easily plug that in. We've got integer variables for our sensor value and our servo value. We're creating our servo variable, and keep in mind this can be named whatever you want. Servo 1, 2, 3. You can even give it other names, though having servo in the name is going to make it easier to read your code later. In our setup, we're attaching our servo. First thing we'll do is read our analog sensor, and before, for our PWM, we were mapping from our analog sensor value 0 to 1023 all the way from 0 to 255. In this case, we want to map for our servo min pulse to our servo max pulse. If you wanted to use servo.write with degrees, you would change this to 0 to 180. But again, the basic idea is that 0 becomes servo min pulse 600, 1023 becomes servo max pulse 2400, and anything in the middle is mapped linearly between those two. Servo1.write microseconds, just like in our previous example, will write whatever value we've read from the analog sensor and mapped to our new range. And then we've got a short delay to account for servo movement. Let's go ahead and upload our code. So here you can see as we turn this knob, our servo position is going to change. Let's say we brought this right in at 90, went back to our logic analyzer, start recording. As we can expect, our pulse is right around 1500 microseconds or 1.5 milliseconds. Let's bring this over to 135 degrees. Try reading that. Here our pulse is 1.917. As we'd expect, that pulse gets bigger and bigger as we go all the way to 180. Here, all the way up to 2.4 milliseconds or 2400 microseconds. Now you might notice that I'm turning the knob counterclockwise and the needle points clockwise, and if I turn the knob clockwise, the needle points counterclockwise. So this is just because of the physical construction of the knob compared to our outputs. And I'm going to show you a quick trick on how you could reverse that. So the easiest way is here in the map function, where we're going from 0 to 1023 to 600 to 2400. If we reverse these values so that max pulse is first and min pulse is second, 0 now maps to 2400 and 1023 maps to 600, reversing the mapping. It's still linear, but we'll get a reverse mapping. So let's go ahead and upload this. Now the knob turns in the same direction as the servo. This is just one way that you can do this. You can also do this here in this analog sensor by inverting this. So that would be 1023 minus this analog read. Or you could invert it down here before you write your microseconds. This is just a quick and easy place that you can invert this data. So let's take a look at File, Sketchbook, RobotGeek Sketches, RG101, Servo. We're going to skip over continuous rotation for just a second. If you're interested in seeing the actual values, you can run this analog in servo out serial and then read the serial data just like we have in other videos. But right now we're going to look at Detach Servo. The Detach Servo sketch is going to work on standard RobotGeek servos that are Generation 2 servos. And you can tell Generation 2 servos by the white cable on their servo. So this is everything new that we sell from RobotGeek. Some of the very early servos had another black cable with a single white band. Those servos were not going to support this detach function. So in this video we have our constant integer pulses. We have our servo pin and our button pin, 3 and 2 respectively. We have a servo value that we're going to start at the min pulse, 600. An increment of 100, we're going to automatically increment this servo back and forth, so we're going to move by 100 microseconds. Start our servo object. Our button is a pin, is set as an input. We've attached our servo to servo pin, that's pin 3. First we start by writing the servo with its microseconds, its min pulse, that's 600 microseconds. That'll go to 0 degrees, and we have a delay of 3000. So what we're doing here is just a scan. We're going to take our servo microseconds, write it to the servo. We're going to increment it by that increment. So it starts at 600. It's going to add up to 700, move a little bit. This is similar to our fade sketch, our fade up sketch in our PWM, where if the servo goes past a certain bound, it's going to change the increment. Only this time, instead of resetting, we're going to invert it. So if the servo value is less than the minimum pulse, or the servo value is greater than the maximum pulse, the increment will now become negative, whatever it is right now. So servo value starts at 600. It goes up by increments of 100. So once it gets to 2400, or that servo max pulse, this if condition is going to be true. So if the servo value is greater or equal to servo max pulse, if 2400 is equal to 2400. This or statement means that only one of these needs to be true for the entire phrase to be true. So once this becomes servo value is 2400, this becomes true. This entire if statement becomes true. And then servo increment will now become negative servo increment, so negative 100. That way when the loop comes back, it'll start decreasing. Once it gets down to 600, servo value will be less than or equal to 600. Again, making this whole thing true, and our negative 100 will become positive 100. We'll wait a short time to move before we go to our next loop and write the microsecond. And here's where we're actually going to detach the servo. So we're saying if this digital read button is high, then detach the servo. When you detach the servo, it's basically going to tell the servo to stop accepting commands and to turn its motor off. So this can be really handy if you need an emergency stop on your servo, or if there's some other reason that you need to stop sending signals to your servo. Remember, the servo is going to want to stay at the last signal you've been sending it, so if you set it here to 115, it's going to be really hard to move the servo's position. So let's go ahead and run this sketch. Now that the sketch is uploaded, you'll see the servo moving back and forth, back and forth. I'm going to press the button now, and the servo is going to stop. but I can still move the servo by hand. It's not static and stuck anymore. Now if we take a look at the logic analyzer, we're not going to see any data coming through. So this code is still running. It's still running write microseconds. It's still changing these servo values. If we were to put in serial prints, it would see all the data coming through. But because we've detached the servo, the hardware knows to actually not send the data anymore. The servo just stays low, telling the servo that it should be off. Now, there's still a lot to learn about servos. We have advanced libraries like Servo EX that will allow you to control multiple servos together and do interpolation. There's also a lot to learn mechanically. Part of that is learning about how servos connect together, how to build your robots, and part of it's learning about the physical characteristics of the servos, the motors, the gears, the control board, so that you know what kind of accuracy you should expect out of servos. But with this basic knowledge of how to use the basic servo libraries and servo functions, you're well on your way to getting started in robotics using the RobotGeek system.